In this video, the starting point is this ordered differential equation for the DC motor. So it's given via this second order ordered differential equation. And you saw the DC motor here just effectively rotating to a given angle. This ODE effectively describes the dynamics or the motion of that. So this DC motor example was first introduced in part 4 of the videos on transfer functions. So what we're going to do is we're going to undertake the transformation, the Laplace transformation, because eventually what we want to do is obviously put this into transfer function form. So we're going to use equations 2.2 and 2.3. These were determined, so equations 2.2 and 2.3, these were determined in part 2 of 4 of the video. So if you're not familiar with these equations, the Laplace transformation for the first derivative and what that becomes from the time domain into the complex frequency domain, the second derivative, and what that becomes in the complex frequency domain of Laplace, have a watch of that video, why that transformation occurs. But so what I said, what we're going to do is undertake the transformation. So if we're looking back over here at this equation, so if we look at the second derivative here, so d squared and then this theta of t, dt squared, that effectively is given by this rule here, where y of t here is the output, here it's just theta. So that becomes effectively d squared over d squared t becomes s squared. This coefficient here in front, so you can see here, this obviously remains, so this is given here, and then we've got then theta of t, which here you can just see becomes theta of s. I've just decided to keep the notation here of theta, that's fine. Then this part here, so this number here is going to stay, and then we've got obviously d by dt. So if we look here at the first derivative, d by dt effectively becomes s, so we've got s here, and then y of t in our case is theta of t, that just becomes there theta of s. And then v subscript in, so that's to denote voltage in, so the input to this DC motor is voltage, becomes v subscript in of s. What I notice is obviously we've got theta of s that are common to both bits here and here, so what we can do is put that outside the brackets, and obviously because it's common to 2, and then put the coefficient with the s squared and the coefficient here with the s here inside the brackets, and that's just equal to the voltage in. So that there is the Laplace transformation. And obviously, as you recall, and you've hopefully gone through the other examples now, you're starting to become familiar that the Laplace transformation effectively enables us now to algebraically manipulate this equation to get it into transfer function form. And the transfer function form is given by equation 2.5 in this video, or this part 3 or 4, this video on transfer functions. So what we want to do is put that into the form of output over input. So in this case, the output is this theta of s, which is your angle, and the input is v subscript in, which is your voltage input. So what we do is effectively take this equation that we've just determined, cross multiply that by this 1 over 0.00875 s squared plus 0.0298889 s. And then what we end up with is this equation where effectively we've got the output here, the angle, being equal to the voltage in, and then over effectively the model for the DC motor. Then what we do is cross multiply by 1 over voltage in. So cross multiply, so multiply this side and then this side by that, and then what you'll end up with is obviously theta s over v subscript in of s is equal to, and then what you'll see here is it's equal to this here, because what you would have originally ended up with is 1 over 0.08795 s squared plus, and then this term s. But because what we want to do is we want to make this leading coefficient utility effectively 1. So we want to make this leading coefficient here 1. So what we do is divide the numerator, which in this case would have been a value of 1, divide it by this value here, and also then divide this coefficient value here by this. So 1 divided by this term here is going to give us 1 113.7, and then this term here divided by this number is going to give us 3.398s. Right, so this in the terms here, this is a slight typo there. This is G subscript A, okay, because it's the actuator. So DC motor is our actuator, and you can see here we've got G subscript A for the actuator. Input voltage in, output is the angle, and then you can see there the transfer function that we've just effectively determined based on this original ordinary differential equation. So I hope that's helpful. If there's any questions, please feel free to contact me. Thank you.